Right now, you are looking at a live transformation. We are taking an ordinary, mark-losing revision plan for your Cambridge IGCSE Physics 0625 energy topic and instantly upgrading it into a top-band scoring system. Because let's face it, if you're sitting your exam soon, you literally cannot afford to leave your hard-earned marks to chance. In this explainer, we're going to completely strip away the fluff, reverse engineer the examiner's exact mindset, and secure those critical grade boundaries that you absolutely need. Okay, let's dive into this. Take a close look at this calculation. Work equals 50 times 2 equals 100. I mean, it looks mathematically correct, right? Well, in a Cambridge physics exam, writing this down is a painful learner mistake that will actively cost you your grade boundary. You might fundamentally know the physics, but right here, you are failing the exam technique. The examiner absolutely cannot give you full marks for a naked number. You're leaving valuable method marks entirely on the table. And honestly, when the stakes are incredibly high, missing these foundational components is exactly what drops a student from an A down to a B or a B down to a C.
So here is your first quick win to fix that. Instead of just jumping straight in and writing W equals 100, we explicitly write out our formula, W equals F times D. Then we meticulously substitute our values with their standard units, so 50 newtons times 2 meters to arrive at a final answer of 100 joules. By simply stating the equation, substituting the values clearly, and adding the standard units, you completely transform a high-risk, zero-mark gamble into a guaranteed method marks. Think about it. Even if you panic and punch the wrong numbers into your calculator at the very last second, the examiner can see exactly what you tried to do and will award you marks for the process. Stating, substituting, standard units. Lock that into your memory right now.
Now, every physics student knows this definition, right? The principle of conservation of energy. Energy cannot be created or destroyed, only transferred between stores. It's completely foundational to the syllabus. But here's the trap so many of us fall into. Simply memorizing this definition is exactly where ordinary revision fails. You can probably recite this in your sleep, but if you don't know how to systematically apply it to a complex, multi-layered 4-mark explain question, knowing the definition verbatim just won't save you. You need a reliable, repeatable system to translate what you memorized into exactly what the examiner wants to read.
And that brings us to the core 4-step framework for structuring your explanations to perfectly satisfy those Cambridge mark schemes. Whenever you face a written explanation question, please do not just start writing a paragraph and hope for the best. Follow this exact sequence to build your answer. Step 1. State the underlying concept, like the conservation of energy. Step 2. Pull evidence or data directly from the specific question, graph, or diagram in front of you. Step 3. Connect those two pieces with clear scientific reasoning. And Step 4. Polish the entire sentence using precise examiner wording. This structure acts like a fail-proof checklist in your mind. It guarantees you hit every single marking point on their page.
In a moment, I'll show you the examiner clue that changes your efficiency answers completely. But first, you need to see how this framework makes that clue obvious.
Let's apply our new framework to a typical practical investigation. Here we have a classic cooling curve data table. As you can see, time is ticking up continuously to 60 seconds, while our temperature drops rapidly from 80 down to 45 degrees Celsius. In a practical test, or an alternative to practical paper, the examiner will ask you to explain what's happening here in terms of energy. And you know, without a system, most students will just look at this and write down the very first thing that pops into their head.
Which leads us directly to this terribly common answer. The heat goes into the air. I want you to spot the error here. Why would a Cambridge examiner look at this vague sentence, immediately cross it out, and award absolute 0 marks? Well, it's because it completely ignores our 4-step framework. It lacks correct scientific concepts, it relies on everyday conversational language instead of precise physics terminology, and it completely fails to reference the specific thermal system properly. Now look at the transformation. Here is the ultimate top mark band answer. Thermal energy is transferred from the hotter water to the cooler surroundings. Notice the massive difference in quality there. We didn't just say heat, we used the specific correct term, thermal energy. We didn't say it just goes, we specified that it is transferred, and we actively identified the exact temperature gradient from the hotter water to the cooler surroundings. This is what we mean by scientific reasoning combined with exact examiner wording. This is exactly how you play the game and win the grade. So the crucial point is that it's incredibly easy to bleed marks if you aren't paying close attention to the details. Let's rapid fire through the absolute most common, mark-draining pitfalls students stumble into during practical energy experiments. Treat these like hazard warnings, okay? Missing units on your final answers, that's an instant penalty. Premature rounding, meaning chopping off your numbers halfway through a multi-step calculation instead of waiting until the very end. Vague explanations, just like the one we just fixed. Graph axis errors, like accidentally swapping your independent and dependent variables. Identifying the wrong control variables entirely. And giving weak, non-specific improvements to an experiment, like writing, use better equipment, instead of a specific action like, add a lid to reduce thermal energy transfer. You got to avoid these traps at all costs.
And this brilliantly illustrates the exact same principles when we escalate the stakes and move into power and efficiency data analysis. Check out this energy bar chart. We've got a total input energy of 500 joules. Out of that, we get a useful output energy of 200 joules and wasted energy, which is likely dissipated into the surroundings as heat and sound, of 300 joules. All the data is right there, beautifully following our core conservation of energy principle. Because, of course, 200 plus 300 equals 500.
Now it's your turn. I want you to pause and predict. Using the exact data we just looked at, 500 joules total input, 200 joules useful output, calculate the efficiency of this system. Run the numbers in your head or jot them down on a piece of paper. Think carefully about your final answer. What exactly are you going to write on that final answer line to secure all the available marks?
Here is the earlier teased examiner clue. Did you write down 0.4J? If you did, you just lost the final accuracy mark. Think about it. Efficiency is a ratio. It is useful energy out divided by total energy in. Since you are mathematically dividing joules by joules, the units completely cancel each other out. Efficiency has absolutely no units. Adding a J to 0.4 is a classic, devastating error that examiners are specifically trained to look for just to penalize you. The correct answer is just 0.4, or if you prefer formatting it as a percentage, 40%. You must always do a final practical check on whether your answer actually requires units.
To recap what we've covered in this explainer so far, let's look directly at the examiner's own expectations, straight from the source. They state clearly, strong answers include correct terminology, substituted values with units where needed, and conclusions supported by data. It's not just about fundamentally knowing that energy is conserved. It is about relentlessly proving to the examiner that you can communicate that conservation using their highly specific language, formatting, and strict rules.
Having the framework is fantastic, but let's see how this builds into an even bigger challenge. You've mastered energy transfers now. You have the ultimate 4-step answer framework. You know exactly how to check your units and avoid premature rounding. But what happens when you misread the crucial command word? What happens when a multi-mark question explicitly asks you to evaluate an energy resource, but your brain accidentally reads it as describe? If you answer the wrong type of question because you misunderstood the command word, your perfectly sound physics will still score 0. And that is exactly why mastering command words is not optional. It is an absolutely required part of your exam survival toolkit. In our next explainer, we are going to tackle this exact problem head-on. We're going to take a whole paragraph of a flawed student answer and transform it live by simply decoding the tricky command words those examiners love to use. It is the mandatory next step in your revision map.
Look, if one misplaced letter J or a slightly vague sentence can cost you your grade boundary in basic energy calculations, ask yourself, how many marks are you unknowingly bleeding when facing complex evaluate questions? To make sure you don't miss that crucial upgrade to your exam strategy, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click on the next explainer right now and let's keep building that top band scoring system together. See you there.